All right. So what I asked you to do through SDS, I introduced you to the notion of repeated sampling. And I begin by using the binomial distribution and seeing the binomial distribution like a sample, where n is the number of trials, the probability of a success of seeing what you're looking for is known, and then there's some really tidy results that follow. And so this is one of the main results that we use. I spent some time discussing the normal distribution and explaining that there are, the binomial distribution, and explaining that there's an instance where you find that the binomial distribution can be approximated by the normal distribution. The first characteristic that we need to the first characteristic of a normal that we're after is the symmetry. And I explained to you that a binomial will be symmetric if P equals 50%. So the probability of success on any independent try is 50%. Or then I introduced this, saying that also.
Excuse me, Professor. We just see the model. I'm not sure if you're writing those things that we should be seeing.
Yeah, I am, but let me see what happened. I'll just stop share first. I'll start over. I think I have to. I can't remember these cables. In the right slot. Okay. Thank you. So the binomial distribution is symmetric in shape if the probability of success is 50%, or if n times p is greater than or equal to 10, or n times 1 minus p are greater than or equal to 10. So mostly I explained to you the theory, or where the theory comes from. This result that you need these to be true is something you just have to remember, okay? That p equals 50%, you can see that because you know the pattern of a binomial, and we can see that it's going to be symmetric when p is equal to 50%. And you can even look at that in Excel. You can see that in the tables that are derived, that when you have p equals 50%, no matter what the n is, you're going to have symmetry in the distribution. Alternatively, you can also find symmetry if there's this relationship between the size of the sample, or the number of trials, in other words, n, and the probability of success. So if these both are true, then we can approximate the normal using the binomial. And the reason we want to do that is, well, I explained at the end of last class that before we had Excel as a ubiquitous tool that, you know, people had it on. Now that people have it on tablets and computers, and everyone has a computer in their home. Many people do. It wasn't the case before, and statisticians had developed tables with a variety of binomial distributions on them. And if the particular one you were interested in with a large number or large size n wasn't available on a table, you'd have to derive it by hand. So statisticians developed approximations to do this much more effortlessly. And that's where this idea of identifying when you could do the approximation, where it rose. So that I spent some time practicing solving problems where, and ultimately I want to get to the ESP problem here, page 19, where we finally answer the question about ESP. Now, to see if a person just guessing, what's the chance that they actually would be found to have ESP? In other words, we want to find out what's the chance that a person can correctly guess 50 or more cards if they have cards of with different shapes on them by just thinking about it, not actually seeing the card image. And then to solve this, rather than doing a table in Excel, I use the approximation. And in the approximation, so what I'm going to do now is just show you the summary. The summary is this document here. So this is your formula sheet. This is what you're going to need by your side for the next few weeks. And yeah, you're going to have your notes, and you're going to have all your resources at your disposal. But if you understand this document and how to use it, you're going to excel in the final exam. Okay. So here you have a summary of the formula. We begin here with the binomial. So this covers, number one, covers the bin. If X has a binomial distribution with parameters n and p, then X has a mean NP and a standard deviation NP1 minus P. And if you didn't understand why, go back in the videos and watch, because I explain that. So just make a note for yourself to go back. And then the probability for that X, or the number of successes, is precisely a value where X can take on 0, 1, 2, all the way to n number of successes. To solve for any one of these, you use the binomial formula. And then I make a point that X is also approximately normally distributed, provided this is true. All right. So in other words, you could use this to calculate the probability for each one of these and add them up. Or if it's true that you have a large enough sample size and a proper P so that multiplying them is greater than 10, and you have a large enough sample size and 1 minus P multiplying them is greater than 10, and you're talking about a large population, and you'll see I'll mention the population is large. So for large populations, this is true, that X is actually approximately normally distributed. And then I spent some time solving problems, and then I resolve those problems using a correction factor. That's what I've spent some time. So I just repeat solving the same problems. In this case, for the problem of ASP, rather than saying x equals 0, 1, 2, 3, 49, 50, 51. And having to sum up, compute and sum up all of these. Rather than doing that, we're going to use the normal distribution, because it's true that n times p is greater than 10 and n times 1 minus p will be greater than 10. And so then I say that x converts in approximation. I use the symbol for approximation into a normal where the mean is n times p. And like I said, go back if you don't know why. And this is np 1 minus p square root. So you should be familiar with those numbers in relation to x, the number of successes in n independent tries. So I calculate those. I show you how I calculate those in the second step. And then I find them. So here I just show you the answer. Oh, I should write here that this is an approximation. And you shouldn't be overwhelmed if you are comfortable with the normal distribution. I promised you we were going to lean on the normal distribution for the rest of the course at some point. Well, that's what we're going to do here. So I have a mean and a standard deviation. So how do I solve for x greater than or equal to 50 now? Well, it's just a normal. This converts from a binomial into a normal. So all I have to do is standardize and solve. Now, when I standardize this, the x, that becomes a standard normal. When I standardize this, it becomes a number 5.77, which is way off our chart, but we still know the answer, even though it's off our chart. 5.77 might be over here, let's say. And we know it's off the chart, and anything off the chart in this tail, we say it's going to be 0, close to 0. Again, if you have issue, you can check in Excel and see if how many decimal places you get. If you have, as I explained last class, 0.0000, that'll be considered a 0. Okay, so we're only going to stick with 4 decimal places. If it rounds up, 0.0005 would round up to okay. So in scientific notation, as long as the exponent is more than -5 or more negative, that will be considered 0. So the answer is 0 here. So it's in other words, it's going to be very unlikely. Might as well say it's 0 that a person by just guessing will be found to have ESP. It's unlikely by chance someone will be found to have ESP. They actually probably have some skill or some ability. If they turn up to have more than 50 cards, it should be unlikely that they're just normal, or they don't have ESP, or they don't have some sort of talent. Okay, so that's what I do with that. And I do several of these problems. And then I solve them again using the continuity correction factor, which you also can review. If you don't understand that, please let me know and I can look at that with you. So these are just solving the same way. This is the continuity correction factor. How many people got this far? How many of you got this far? I'm going to leave it for you guys to work on that. This is just to say, when we go from a spike distribution and start talking about a normal distribution, there is a price to pay because there's no density here, right? They're just spikes. So to make it exactly normal, or to make it, like to fill in this gap here, to deal with this gap here that exists because of the spike, we have to make an adjustment to include the whole bar or less than the bar. And that's what this whole discussion is about. Anyway, I'll leave that to you because I'm going to spend another half hour there otherwise. Okay, so if you don't follow this, I can look at this next class. And I just solve all of these. And then I recommend these assignments. And then what I do, so I move from the 1 minute here. I do this here. No, that's it. Okay, I'm sorry. Let me see. I feel like something. 1 minute. Okay, here. So what I do here before I go there, okay, so I solve a bunch of problems. Okay, I need to say this. And then what I do is I say, well, usually, so this is slide 20. Usually in statistics, we don't talk about the like it's very useful. The binomial distribution is very useful. Okay. However, it's just a foundation to talk about a statistic that is particularly of interest to us, and that is the proportion of successes, not the number of successes. So X is the number of successes. But if you take, so if you say like 50 successes or more, right? That for the ESP, 50 correct guesses or more, X was 50 or more. But what's the proportion if it's 50 or more out of 100? Patricia, CCF is omitted from the exam, but I still want you to learn it. So it's in quizzes and things. It'll be in Connect. I just can't put everything on the exam. Okay, so number of successes is X. So example, 50 correct guesses.
So Professor, so you just mentioned the CCF might come on the Connect actual assignments.
Yep.
Okay.
It's not omitted for the course. It's just not going to be on the final exam. Okay. So X is the number of successes. What about what we actually are interested in polls? We're interested in the proportion, right? What percentage of people are Catholics? What percentage of people support the Democrats? What percentage of people support a certain policy? What percentage of people survived having, you can say, COVID? So it's a proportion that we talk about. We don't talk about the number. However, we could talk about that, but usually we like the proportion. So to talk about the proportion, what I need to do is take 50 and divide by how many, right, correct guesses are possible. So 50 correct guesses or 50%. Because it's 50 out of 100. In other words, X over N gives us P hat. P hat is the symbol we're going to use for the sample proportion, where this is like the sample size, and this is the number of successes. P hat is the sample proportion of successes. So here's my question for you. I already gave you the answer, but usually I do. So is P hat a statistic? Is P hat a statistic? So think back, what is the definition of a statistic? Is P hat a statistic?
An approximation, right?
Sorry?
You mentioned it was an approximation.
Well, not that I just mentioned, but what is a statistic? What's the definition of a statistic? The definition of statistic, a statistic is a number computed from a sample. Is P hat a statistic? How do I compute P hat? I take X and I divide it by N. Well, N is a statistic because it is the sample size. So it's a number from a sample, number calculator computed from a sample. X is the number of correct guesses, or X is the number of successes in a sample of N or N independent trials. So it's also a statistic. So X is a statistic, P hat is a statistic because they're numbers calculated from a sample where the sample size is N. Okay, so yes, it is a statistic. What about X? Is X a statistic? To sort of, full circle here. First class, we discussed what a statistic is. These are all statistics. Okay, you're computing them from a sample, and they have theoretical properties. We have assigned them theoretical properties. So X is a statistic with a distribution that's binomial with parameters n and p. Wrap your head around that one. Then p hat, the question now becomes, what's the distribution of the statistic p hat? So this whole discussion is SDS. It's the sampling distribution of a statistic. That's what we're talking about right now, the sampling distribution of a statistic. So X has this sampling distribution. What does p hat have? Well, p hat is equal to X divided by n. So we need to find what's the mean of p hat and what's the standard deviation of p hat. If X is approximately normal, if it has these properties, so this is only true, remember, because it has this property, and times p is and minus 1 minus p are greater than 10. That's the only way I can do this. Then you'll see exercises where it's not true, and you have to go back and use the binomial distribution, not the normal. So let me add here. I'm squeezing this in. I don't know what I'm thinking here. Let me squeeze this. Sorry. You see that? I'm gonna have to make it bigger and do it because I'm not succeeding. Okay, so since the properties are true, then X is approximately normal with mean NP and standard deviation NP1 minus P square root. Then what about P hat? How do I find the mean and standard deviation of P hat? Well, because of the rules of means and variances that you learned in module 8, in fact, all you have to do, just like you divided X by N, you just divide the mean by N and the standard deviation by N. And it follows through that this is going to be P, and this is going to be P1 minus P over N square root. And I do the math below to show that. And even though I spend a lot of time talking about the number of successes, I really focus on the proportion of success and this sampling distribution of this statistic p hat. So if I know P, the probability of a success, I can do all of this, right? I can understand the sampling distribution and approximation, if this property holds, and I can make predictions of what to expect in the sample. So I have some questions here, and I say, okay, so again, back to the ESP example, rather than asking about what's the chance that 50 out of 100 correct guesses or more are made, what's the chance of that happening? Well, I'm going to ask instead, what's the probability that the proportion is more than 50%? It's essentially the same question. And I go through the same sort of steps. I calculate the new, the mean for the p hat, which is just p. So what does this mean when you think about it? It means that on average, given that you're told that the probability of success is 25%, so given that the probability of success is 25%, remember for the ESP example, on any individual guess, 25% of getting the card, guessing the card right, then on average, if I'm to do this again and again and again, on average, the distribution of this phenomenon, or the distribution of this statistic, which would be determined empirically, you could repeatedly try it, right? You could do it again and again and again, repeating this, asking 100 times of a person and then repeating it with another person and asking 100 times and repeating with another person and doing this again and again and again and again. The first person might have gotten so again, imagine an Excel sheet. So your first sample, you get a bunch of data, and let's say the first person got 35% correct. And then the second person got 40% correct. And the next person got 10% correct. And the next person got 6% correct. And the next person got 10% correct, and so on. So I do this, I repeat this many, many, many times. On average, if I was to average all of these, then P, which is the true proportion, in other words, for all possible samples, theoretically, the true proportion would be 25%. And the standard deviation of those could be calculated this way. So if you know P, you should be able to know something about P hat. So in the sample, what's the chance of getting 50% or more correct? You'd have to standardize that with its mean and standard deviation. Standardizing, and you see I have the same, exactly the same number. I should, because I didn't change anything. All I did was I talked about the proportion rather than the number of successes. So it's kind of circular. You get the same result. I repeat the same problems to show you that it is the case. And so that's what I do here. And I make the point that the continuity correction factor is used for X, the count or the number of successes, but we don't do a continuity correction factor for P hat. So that's why I discard it for the exam, final exam, because, well, in fact, I mostly solve problems with proportions in the end anyways. Okay, so just to make a point here, if I solve all these, I think I say here that the continuity correction factor is only applied with the count variable X, not with P hat. So we call this X the count variable. All right, so it all make more sense when you go through that material. All I'm doing is converting the binomial into a normal distribution and returning to the normal. The only step that you have to be careful about is calculating, not careful, but the actual calculation you have to make is for the mean and standard deviation of the normal variable in approximation. So I have a bunch of exercises you can try, and that brings us here. So all I've talked about so far is summarized here, where this bracket here is really SDS for X. That X is approximately normal with a mean NP and a standard deviation NP 1 minus P square root. So that, again, those parameters, it's all you need to describe that variable. That brings us to P hat. The sampling distribution of P hat has a mean of P and a standard deviation of P times 1 minus P over N square root. That looks remarkably the same as this. All I did was divide them by N, and I got this and this. So this, number 2, is all about SDS, but on P hat. So that's the sampling distribution of a statistic P hat. And then that's for sample proportions. And then I go to talk about the sampling distribution of the sample mean. And I spend some time on that. So this is SDS on the sample mean. So the idea here is that if a variable has a mean given to you and a standard deviation given to you, see, they're both given, they're known, then what can you expect in the sample? That's the question. What do you expect about the sample mean in particular? And So this is like if you've ever had your blood pressure read with a machine as opposed to a nurse, your blood pressure will be measured with this machine. Has anybody had that, a blood pressure measure with a machine? Their blood pressure measured in the machine will measure it several times, not just once. Because it was determined that when people sit down and they're, they either come to emergency or they're having their vitals checked because of concerns, they're nervous, they're uncomfortable, right? They need to relax into it. Just getting one blood pressure reading, is that really accurate? How accurate could that be? So instead, they have the machine read it, with a color scale. The machine will read it several times, 3 or 5 times, and then it will report the average. By doing that, that average is much more stable across those that sample than any individual number that was determined or calculated, or not calculated, but measured. Okay, so how do we see that in theory? Well, if your blood pressure is the variable X, you could sit there with that machine ad infinitum, right? It's not practical, but you could, and then you could make a histogram of all those measures and calculate an average and call it the mu, because that would represent the population of all your measures. And you could calculate a standard deviation and call that the standard deviation of the population of all your blood pressure readings. And what I'm really interested in is the average of doing that several times. So just like I did with the p hat, so I'm going to do it here. So let's say I have sample, and then let me do it. I'm going to make this bigger. Okay, so let's say, first of all, we have to establish sample size n. So they all have to have the same sample size. So we'll say this is sample 1, and let's say your blood pressure, well, there's 2 measures in blood pressure. So let's say, let's just do this with something that has variation. And I have many examples. Let's just do it with the first measure of your blood pressure. So 181, let's say 167, 160. So you do this, whatever n is, that many times, right? And you can calculate an average, whatever, let's say 165. And I want to make a point here because I'm going to do this. Okay, so then let's say we repeat the sample. So we repeat it. Let's say, this can be done in critical care or an ICU. I'm not sure what you call it here in Puerto Rico, but in intensive care, right? In the hospital, and you have a machine measuring this over time. So this will be your average over the first set of readings, but then you repeat it later in the day. And you get 172, 165, 166, 180. And then they average it again, 171. And then you repeat this throughout the day. We'll refer to it as all possible samples. So there's this sample, the set of samples that we're talking about. The important thing is that these X bars have a distribution. Okay, so here's a question for you. If you've done this before, if you've already read this material, does this distribution of this set of X bars, does this distribution depend on N, the sample size, or does it depend on how many samples you took? What does it depend on? And what is the shape of that distribution? So just doing this, just writing this, what do I know?
Yes, as you're doing average, it tends to a normal distribution, right?
Well, I'm asking you. Does it?
Shouldn't it be symmetric?
Should it be symmetric? So you have a sense that there should be some stability, right? There should be some sort of stability in these numbers. These numbers are less volatile than these numbers. So the shape should be more regular, should be symmetric. Should it be normal? What would make it normal? Does it matter what how the X's were distributed? So these are all the questions that arise. What can I expect in this distribution here of this person, blood pressure readings? The distribution of the X bars, what does it depend on? Okay, so that's the answer. So the answer is the next bullet, number 3. If X has a mean mu and a standard deviation sigma, now notice I didn't say anything about the shape yet. So if you begin with blood pressure reading for a person, and you know their population mean blood pressure reading and the standard deviation of those, then the sampling distribution of the sample means will have the same mean. So on average, the average of this distribution should have the same average of whatever the true mean is for all the blood pressure readings possible. But the standard deviation is this, and it depends on 2 things. It depends on the standard deviation of the blood pressure for the person. If you know that, you should know that to do this, and the sample size. So you are right to say, Patricia, that it's the sample size that matters. So I didn't say anything about shape yet. All I've said is if you know the mean and standard deviation of that variable, in this case, the blood pressure readings for that person, then the sampling distribution of the sample mean, so these will have the same mean as the original, but a smaller standard deviation that it's going to be smaller. So in other words, these are closer together than the original values by a factor dividing by square root of n. So it depends directly on the sample size, not on how many times I repeat this, okay? It's the sample size that matters. So in other words, the greater the sample that you take each time, the smaller the variation, the more stable the sample means will be, the more accurate you're going to be, because your each one that you take is closer. So each sample you take will be closer to the true mean mu. So that's the idea. You want to estimate, you want to take a sample that represents the population. So the larger the sample size, the better chance you're going to have at getting to the real true sample mean. Now, one catch here is this is not an issue of estimation. I've given you the mean already for the population, and I've already given you the standard deviation. I'm teaching you how to use these givens to anticipate what you see in the sample. And I'm doing that. I'm teaching you this bridge to go from the variable to the sample, because what I want to do is I'm going to take away the knowledge and go backwards, which is more realistic. We start with a sample. We don't usually start with the information on the population. That would be ridiculous. Why would we take a sample? Why would we take a sample to estimate mu if we already knew mu? Okay, but I need to build that theory so that then I can say, well, in reality, we don't know mu. So if we take a sample, what do we really have? Do we have anything worth anything? And that's what inference is for. Inference is the theory of what can you expect in your population if you have a certain sample. We're going backwards, in other words. So I'm going to talk more about that in a moment. So the last thing I want to say about this is, what about the shape? I haven't said anything about shape. I didn't say anything yet. So what about the shape? If you know that the distribution of the blood pressure for this individual is normal, then the distribution of the sample means will be normal. If you do not know that the distribution, because that's, again, that's more realistic, you don't know, right? So if you don't know the distribution of the blood pressure readings or whatever it is that you're measuring, if you don't know the distribution, what can you say? That's the question for you. It's in the bracket, but I need you to understand it. What does it say there? So it's not just about symmetry, it's about normal. If X is normal, X bar is normal. So this will have a normal distribution. But if X is not normal, as long as the sample size you take is more than 25, we can comfortably assume that this shape is approximately normal. A very important assumption. It has an important name. Not an assumption, but an approximation that has an important name. What's the name of that theory? You guys didn't get this far? Call the central limit theorem. Very good. Thank you. Yes. Okay, so just that part. If you don't know the sample size, I mean the sample or shape, the shape of the distribution. Yes, central limit theorem. Okay. So 1, 2, and 3 are bin and SDS, all summarized for you. Okay. If you didn't understand what I said, you will understand what I've just said. You can go back to this video and watch it again and feel confident each time you watch it, more and more confident that you know what's going on. Okay. So the way that I write the central limit theorem. So this is the result. This is just the result, the summary of what I've just said. If you begin with a variable and you know its mean and standard deviation, then the sampling distribution of the sample mean will have the same shape, the same mean, and a smaller standard deviation. This is always a smaller number because you're dividing by n, which is always positive in integer. If you're given x and you just know the mu and sigma, but the shape is unknown, or the distribution, right? Which is realistic. Because why would you know that? So you're going to get the same result in approximation if what? What's missing here? What I've said? What's missing in my second statement? What am I missing? Not 25%. And greater than or equal to 25. I think you just wrote that by accident, right, Patricia? So n has to be greater than or equal to 25. Now, some textbooks will use 30, but 25 is a nice round number when you take the square root. So I just say 25 or more. And a lot of textbooks do too. Depends what textbook you're looking at. All right. So inference begins where I go the other way. What if you don't know mu? What if you don't know sigma? What could you get out of the sample? what we do is we guess is the approach. So we guess at what mu might be. And then we use a sample and we collect a good sample. And we try and falsify our assumption. We try and find evidence against we try to find evidence against our guess. And we're going to use the fact of what we should be able to expect. So we're going to say, well, we expect this. And do we find it? If we think we know mu, do we find what we expect to see? And that's what I'm going to teach you how to do. Okay. Now we're going to do that for the sample. Using the sample mean, but we're also going to do it for the sample proportion. And that's where I'm going to start. I like to start with the sample proportion. If you don't know the true proportion, where can you start in estimation? Any questions? Have I blown your mind? So this formula sheet summarizes all these things, and you might not understand it today or tomorrow or next week. Just keep staring at it. It'll all fall into place. Lots of practice is necessary. And there's a lot of inference we can do. I'm going to just focus on inference on the mean and inference on P, the proportion. When I talk about inference I'm talking about inference or guessing about the true proportion or the true mean, not X bar, not P hat. I use those sample results, however. So we're going to go into the inference notes. And I want to start you, and I'll do the same thing in the videos. You'll see I start here. So you're going to feel like we're swimming at first, or you don't know how to swim. And then we'll formalize a systematic approach. So I'm going to start here. Let's take a 5-minute break. You can get some water or tea or whatever it is you can sip on. Well, I'm going to start inference in 5 minutes.
Professor, and what module are you on right now?
The last one.
Okay, I got lost when you said.
9. Where did I lose you just now?
Yeah, I didn't realize which, I saw you switch, but I didn't.
Yeah,
know-
no, I didn't. All I was doing before was looking at the formula sheet.
Yeah, the last
That's at
one.
the end of 5, right?
Okay, perfect, thank you.
So, but then I have it also at the end of 6. Same formula sheet. And if you don't understand it and you think I'm just gonna stop talking about this stuff, I'm not. This is how I'm gonna talk for the next 3 weeks about this material, so you gotta get it. Yeah, we'll be back at 10:35. What's this? So 6 is huge. Sorry. Module 9 is a huge module, but it's just because I have all the questions and answers in it. I don't know where it went. Where to go? This is the one. That's where I want to start. Okay, I'm back. Any comments or questions? All right, so here we begin. I'm just throwing you in the water. You don't know how to swim. And I'm going to show you, okay? Or your instincts are going to kick in. That's what's going to happen. And I'll explain why. In a study with a new vaccine involving 53 lung cancer patients, 29 survived 5 years after surgery. The approximate 98% confidence interval for the true proportion of patients surviving 5 years after surgery with the new vaccine has these endpoints. All right. Forget about this for now. Just what do we have? What were we given? In a study, in a study with a new vaccine involving 53 lung cancer patients. What symbol represents 53 lung cancer patients? Close, but not X. Let's read the next part. 29 survived 5 years after surgery. Right, Patricia. So that's the sample. And then 29 survived. Survival is a success in this example. So that means that 53 is our X, sorry, is our N, sample size. And 29 is our X, successes. They survived. Got it? Okay, so the approximate 98% confidence interval, whatever that means, for the true proportion, what is the symbol for the true proportion of patients surviving 5 years after surgery with the new vaccine has these endpoints? So what we're doing is inference on P. The true proportion. We don't have any other information. All we have are N, 53, and X, 29. So true proportion is P. P hat is the sample. Patricia, what is P hat in this example?
Wouldn't it be the proportion of the 29?
Exactly. So P hat is X over N. We have a sample. We have 29 survived out of 53. We don't have any other information. So how many people survived 5 years after surgery? What's the proportion?
.547.
Right. 0.5472. Right. So yeah, get in the habit of keeping 4 decimal places whenever I talk about P in binomial or inference for P. Okay, so that is the sample result. And this is called a point estimate of P. So P hat is a point estimate of P, the true proportion. And Am I happy with that? Am I satisfied? Well, even though we don't have any other numbers here, well, except for the 98% that we're going to talk about, we don't have any other statistics, but we have our theory. And the theory told us that if n times p, which is equal to 53 times, oh, I don't know p, right? I don't know p. And then I can check n times 1 minus p, but I don't know 1 minus p. So what would I do if I had those? I would check if they're greater than or equal to 10 to make sure that I can make a normal approximation. But I can't do that because I don't know p, right? P is unknown. So what I do instead is, because I'm going to assume this is from a large population, I can just assume it away and say P from the theory is at the very least approximately normally distributed with, sorry, P hat is approximately normally distributed. Let me make it a little more hatty, with a mean of P and a standard deviation of n times P times 1 minus P over n square root. So this result, if I know P, should be true, right? But I don't know P. So you see, I keep on hitting up against a wall because I don't know P. So what we do to proceed is I treat this like it's my P because it's the best thing I have. It's the only thing and the best thing that I have as an estimate. And then I build in this theory by saying, well, if that's P, then I can also calculate a standard deviation that looks kind of like this, right? It looks like this. I'm just going to put P hat in its place. And I'm going to build a two standard deviations. I'm going to clarify what I'm talking about. So remember to make usually we say mean plus or minus however many standard deviations, right? 2 standard deviations from the mean, and that should have how many observations should that capture? What percentage? Not yet, Patricia.
95%.
Uh-huh.
95%, right?
Yes. So that's going to be 95%. How many standard deviations from the mean should I be for 98%?
3 standard deviations.
3?
Well,
I want
three.
you to be more precise. How would we find that? How many standard deviations to get 98% of all observations captured? So what did we do? So let's draw a picture. If it's 98% in the middle, how much is it outside?
The remainder 2%.
So it would be 1% on this side. Sorry, and 1% on the other side. In other words, this would be 0.0100. So find the Z to make 98% in the middle. So how many standard deviations would I be away to have 98% within? So you can go to your table. And you're looking for a 1% inside the table, right? So it looks like over here between these two. So you have to be negative 2.3. This one's closer. So that's negative 2.33. Everybody agree to 2 decimal places? So this should be negative 2.33, and this one should be positive 2.33. So it's a little bit further away to get 98% in the middle. So that, what we're going to do is make an interval where the standard deviation is this, but substituting in p hat. And the mean that we're going to use is p hat, substituting the p hat. And that's going to be our best estimate of p. Seems like a circular argument, but it is not, because we're leaning on this theory. So, so what I'm going to do so far, then I have 0.547 plus or minus, not 2, but 2.33 standard deviations. And the standard deviation, I got to calculate that. So I need to find the standard deviation. Let me erase this part, because that's going to be fine. That's going to be handled. And we're going to calculate the standard deviation. So my suggestion is that you do not put the 1 minus in, you just put the value in. So this is going to be 4,528, right? Divided by n is 53, and then square root. So make sure you can get this. Let me know if I made a mistake in my calculation. So you get 0.00467 something, but you have to take the square root. Don't forget to do that. Or you're going to get the wrong option. The 4 decimal places also. Very good. So that gives us times 0.0684. So the best option looks like B. So we have created an interval around the point estimate, P hat, leaning on the theory that P hat has this distribution, and we just estimate. So we're estimate the standard deviation because we don't have P, but we're using the theory to do this and build this interval that has 98% of the possible P's in it. So we say that we have 98% confidence interval for the true proportion. All right, so one thing that's going to stand out is this number is different than this number. But I mean, if you round this to 2 decimal places, this is the best answer, right? But where can I get this number? This number comes from another table that I introduced in Unit 6. I mean, Module 9. Module 9. This comes from this other table that I introduced, and let's talk about that table. It's the distribution of T. Now, T looks a lot like Z. And in fact, for high sample sizes, T and Z are the same thing. So I'm not going to talk about all of this right now. I'm going to just use the last row. So notice for large sample sizes, T becomes C. I'll write it as the variable. T is just the standard normal. And here you have these. So Z star is going to mark where you have, in our case, 98% in the middle. So let me draw that for you, like what we just did. I want to draw this better. So 98% in the middle between negative 2.326 standard deviations from the mean. These are called Z stars. Because the formula that we're going to talk about now depends on uses Z stars, just plus or minus, like I did, mean plus or minus the standard deviation from the mean, number of standard deviations. Z star is the number of standard deviations from the mean. Okay, so that's how we use this for now, where I can just get a certain amount of them. Now, what if you wanted a confidence interval for 97%? What should you do? If you needed the Z for a 97% confidence interval, So 97% is not here. So what you should do is do the way that we found 98 in the first place. You draw the picture, go into the table, and you look for the left side. Okay. Or you can use Excel because you know how to use Excel to do that. Okay. So I'll talk more about the T distribution next time. For now, we're just going to use this row here. Okay, so what we found out is all we needed was a sample. And we can compute a point estimate for the true proportion, p hat, as x over n. So about 55% of the people survived, but because there's variation and another sample would have had different results, we need to make an interval. So the way we make an interval is go so many standard deviations from the mean. And how we decide how many we go is with this language about confidence intervals. So what we're actually getting is an interval of possibilities. Now, the way that confidence intervals work, well, let me write down the formula first, and then you will get this better. Let me go back to our formula sheet. That's not it. I put it here. And then I have to find my formula sheet now. Okay. Okay, back to the formula sheet. So this is what we did. We computed a confidence interval. Let me shrink this. So I need that area. This first column provides a formula for confidence interval. In general, we take the point estimate, which is our best guess, and it's an unbiased estimator. It means in repeated samples, on average, it will be the actual proportion. And we add and subtract what we call the critical value. How many standard deviations you need to be away to get C% in the middle. And this is the standard deviation but because we put an estimate inside here. We have a special name. We call it the standard error. Let me write out the word standard entirely. It's an estimate of the standard deviation. Because I put in p hat into here, but this whole thing is supposed to be the standard deviation of p hat. I don't know p, so I had to use p hat to put in there. So it has a special name called the standard error. These together, this multiplication is called margin of error. You might have heard of that before, margin of error. It's the buffer, it's the plus or minus, it creates the interval. Let's talk about the interval a little bit before we continue. Do you have any questions about this? This is the general formula for a confidence interval that I've applied here, point estimate in this case, because this is inference. So this is inference on P unknown for number 4. The inference on the true proportion. I don't know it, I'm going to guess it, and I'm going to use some theory about p hat to make an interval of possibilities. All these values in the interval are just as good as p hat. So these are all values in here that are equivalent to p hat. I don't have a justification that one is better than the other. P hat is no better than another number in the interval. They're all similar numbers. Theoretically, it's an interval. So I said I would go back. So let's go back to that exercise and talk about the interval a little bit. So I could, if I was to make the upper and lower limit of this, what would it be? What would be the upper and what would be the lower limit? Okay, so Patricia has given us the number 0.3876. Can anyone confirm? And 0.7063. So the estimate is that 40 to 71% of people survive. That's pretty good for people who are desperate to survive 5 years from cancer. Did you have a question? Did I make any mistakes? So again, retain 4 decimal places when you deal with probability.
Yeah, I thought it was 0.7064 because of the rounding.
Let me try. Yeah, it should round to 7.7064. Thank you. Okay, so everyone confirm. Good, good. So looking at our theory again for a moment before we return. P hat is calculated from the sample. What you can change is, well, as a researcher, you could take a different sample size. How will the sample size affect the interval? If you have a larger sample, what will happen to this interval? Will the interval be wider or more narrow? So if n goes up, then this number overall, because you're dividing by a positive integer, the whole thing will go down. So your interval will be not greater, but narrower. Okay, so it'll be the opposite. It'll be narrower. And in other words, better in a way. It's more precise, right? More accurate. You don't have a whole bunch of values. You have just a few. And it makes you a little more sure of what to expect. So it reduces uncertainty. Standard deviation is lower. It's less risky, less volatile, less uncertain. Okay. What happens if you want a larger confidence interval? What will happen to the value? If you leave everything the same, but you change now the confidence interval, what will happen to the interval? It'll be wider. Okay. Now, do you want to be more confident or less confident? What does confidence mean? So thinking about what does confidence mean?
The certainty
Sorry,
is the certainty you have on the results.
In what sense, certainty? Certain about what is our goal, right? Our goal is to estimate P.
Yeah.
So the wider the interval, the more likely that you actually got P in your interval, the real P in your interval. But you lose because every time you make it more confident, you get it wider. So it's a broader range of values. It's less precise. So there's a trade-off. You have to balance that. The convention is usually to use 95% confidence. That's the value, but you're going to practice with all kinds of levels of confidence. And I'm going to do a better job at explaining what a confidence interval does in my next examples. But essentially what you're doing is every time you increase the confidence interval, you're getting, it's become, well, if you increase the confidence, the level of confidence, so this is C%, you can increase the level of confidence, you're getting a wider interval. But again, it's less precise. So if you spent a lot of money on a project, 10,000, 30,000, $1 million on a project, and you end up with a wide interval, it's not even giving you much information anyway. So let's say the example that I kept using was the one about women's heights. Let's say you went to the trouble to estimate women's heights and you came back after $1 million expenditure and told people that women's heights are between 3 feet and 6 feet. Well, we already knew that. That's not precise. You don't want a large interval, you want more precision. But you do want to be sure to catch in your precision, you want to catch the true value, right? The true parameter, the parameter. So let's go back and you guys can think about that. So the idea of a confidence interval is, well, this is one sample. but I could have had another sample. Theoretically, out of all possible samples, 98% of the 98% confidence intervals will actually contain the true proportion. That is the actual definition or explanation of, or application of confidence interval. Okay. So it's about the repeated samples. I have one, but that one comes from a possibility of all possible samples. Just like a statistic is one in a distribution of many, a confidence interval is also like a statistic. These are numbers calculated from a sample. This is statistic. This is just one, but I could have had many. Well, 98% of them will actually have the true proportion inside of it. So we'll talk more about that when we talk about the inference on the mean later. Okay, so that is column number 1. That's confidence interval estimation. I have to give you the level of confidence that I want you to calculate for, and you should know how to do it now. Let's talk a little bit about the margin of error. So this I told you was called the margin of error. So that's the critical value times the estimate of the standard deviation, or we called it the standard error. And let's talk about the question of what sample size is the right sample size. So what sample size should I take to get a certain level of accuracy? Okay. For instance, in general, this is the margin of error. Like I said, this will be given or established. This P also will be given from a sample that's given, or we'll talk about the alternative for P. The choice variable right now that we're interested in is N. What is the right sample size? Solve for N. In general. So to in general solve for N, I'm going to divide by Z star. And then I'm going to, my chapeaus are really bad. Square both sides. And then I'm going to cross multiply because I really want to isolate for N. And so that will mean that I would write Is everybody okay with what I did? Let me move these down a little bit because they're hanging over there. So the right sample size to get a certain level of confidence and a certain level of precision M, remember this is the margin of error. So if I want a margin, let's say if I wanted a particular margin here, I could specify that and find the right sample that I need. In this case, the margin of error is like 15%, right? Or something like that. 2.33 times 0.0684. Yeah. Oh, what a guess. 16%. So this is my formula, but I have to fix it because let's say we don't have a sample yet. So this is the first time we do this. We're going to take a sample. We've never done this before. So C star can be given, M can be provided. But what would be the P? So I'm gonna put a star on it, a lot of stars. It's a different star than the Z star. And either one of these three conditions. So either P star equals P and it's known. So let's say you just knew it. If you knew the population proportion, then to find the right sample size to get a certain level of precision. So let me write that down. So either given Z star and M, either you let P star equals P because it's known, but in fact, we're doing this because we don't know it, right? So we want to get a sample to estimate it. So that's probably not it, but there might be problems like that, you know, it's just testing if you know the theory. So it'll give you P and you can just plug it in. Otherwise, you can use P star from an old sample. A good sample. I shouldn't say good because we're going to assume all samples are good. Even though we didn't think about that when we first learned about sampling in module 3. But we have to assume the samples are good. After we assume we've done the due diligence and gotten a good sample, okay? If you don't know anything about P and you don't have another sample result, then the best thing to do is what? Does anybody know? It's equal to X over N, right? If you have a sample, but if you don't have a sample and you don't know P, so it's like in this order, right? So this is like, this would be your best, this would be second best, and this will be third best. What should you do? You don't know P, you don't have a sample, you have no knowledge. What should you let P star be? I have to let my 2 look more like a 2, not a C. What should you do? No ideas? What we're going to do is just let it be 50%. Let it just go halfway. We have no preference of the proportion. We're going to go right in the middle. We're not going to get into how good or bad a guess that is, but we're just going to use that as our substitution. Okay, so this is our formula for sample size estimation, the right sample size to get a certain level of precision M and a certain level of confidence C star. Don't forget to square. And don't forget about this conditions for what P star is. So let's do a problem now. There's a problem at the bottom. No, there's a problem over here. Oh, and I have a note that you always round to the nearest whole number, and we'll talk about that. Okay, try this one. Oh, let me get the formula over here. I'll take it over here. Any answers? Any questions? Okay, so M. M is the margin. You're not told about the margin, you're given W, the width. What's the relationship between the width of the interval and the margin? What's the relationship between M and W?
The wider the interval, the bigger is the margin of error.
Well, there's a direct relationship.
Yep.
2M equals W. Right? Two margins makes a width. That's the interval. So you're told that the width is 2 percentage points. So what should the margin be? 1%. So they're not the same, but they're directly related. They're double. 2 M's make a width. Right? It's a margin. A little bit of that, give or take. That's 2. Right, so you have to use a P of 50%. And a Z star for 95%, which you will see is 1.95, right? Is it? Hold on. Let's go back. 1.645. Let's look at the table. Let's go back.
1.960.
Oh, 96. What did I say? 95. Okay.
Yeah,
So you got that from the table, right? So you went here and 95% is 1.960. So you can use this table. That's the easiest way to get the confidence, the critical value for the confidence level. So 1.960. Okay. I knew that. Just slipped my mind. Okay, not 95, 960. All right, so we have all those values. Let's put everything in the formula. We know where the formula comes from. So N is 1.96 divided by 0.01 square times 0.5, and then 1 minus 0.5 is also 0.5. And the number that you get is 9604. Now you have to choose which is the best alternative. So the best alternative, the closest one is E, but is that the right approach? So the best answer seems to be E, 10,000. What if the options were instead like, which one should you pick? I think I have to change another one too. Hold on. Change this. Okay, I'm going to change this one. I'm going to leave that one as 10,000. Let me go back. Make my point. Okay. Which one would you pick?
E anyways, because it would round up.
Okay. Oh, here, let's do this. Wait, let me make it like this. Hold on. Trying to make my point when I'm failing miserably. Okay, so which one would you pick here?
So D now.
Huh?
I would choose then D because it's only like 100 above.
Okay, so this is the issue, right? The issue is, do I round up? Do I round down? And I have a note above saying to round up. Why am I saying that? And what's the principle? The principle is, for this type of a problem, that I want to maintain a margin of 1% because I want precision. So it should be 1% or lower than 1%. It's not arbitrary. I want it to be 1% margin or smaller because I care about the precision. So without saying it, that's kind of like what we're saying. You want that level of precision. So which option will make it be 1% or smaller? If those are your only options, you couldn't do anything in between, this one or this one.
Well, if you divide the 9,604 with the 9,500, it will give you 1%, I think. So we could choose that one.
Okay, so the issue is that if you look at the formula, if we go back to the original formula, it makes more sense over here for margin. So what happens the larger the sample size? What happens to M? When will M be smaller?
As N is larger.
If N is larger. So as N is larger, right, Patricia? As N is larger, M will be smaller. So now I'm going to ask you, which one is better, D or E? So E, right? Even though D is closer, if you put this number in there, your M is going to go over 1%. Okay, so that was my point, is that you have to round all the way up, but why you have to round up is to maintain the precision. If you have to choose, you got to go to the higher number. Okay, so it's not like traditional rounding where you'll go to the closest, you know, if it's under 5, you go down. It's not that. The rounding for sample size estimation is to round all the way up. Okay, so you're gonna have more practice with that. So that was column number 2. So column number 2 is all about sample size estimation. So I'm going to squeeze that in. And you have to review those details. Okay, and they're in columns because I'm going to talk about other things. So here, this inference on the proportion, the true proportion with the true proportion unknown, of course. This is going to be inference for number 5 is inference on the mu, and sigma is known. And 6 is going to be inference on mu, sigma unknown. And we're going to talk about those next time. All right, let's talk a bit about the last column. Maybe I'll do a problem and then leave it at that. So this, exactly what I talked about today, is in for sure in the videos. But it's not, there's no harm in repeating this. Okay. So the last column, and you'll notice in all of the columns across row number 4, there is no P. We have a P hat, we have a P star, and here we have a P hat, and we have a P 0. So we're going to talk about P sub 0 in a second, but we don't have P, so this P is unknown, right? So what are we staring at here? What do you recognize here? What is this? Let's be comfortable with these formula. What do you recognize? Let's dig into this. So the denominator is the inference on P unknown. The denominator is close, not the inference, but not the inference, but what is this? We did this calculation somewhere. Where did we do this calculation? Well, we did it over here, right? What was this called? You're onto something there, Patricia. So what is this again? Not the whole thing, just this part. It's called, this part is the standard error, right? It's the estimate of the standard deviation of P hat. It's weird, I know, but it's the standard deviation. All right, so this is like the standard deviation. And then what's happening over here on the top? What is Z? What do we usually, how do we get Z? What is Z? Z is equal to X minus mean divided by standard deviation, right? Isn't that what this is? Okay, yes, Z star is critical value. Patricia is right, it is. Z star is a critical value, but Z in general, the standardized value, right? The Z score. It says X minus the mean over the standard deviation. Is that correct? Yes,
Yes.
yes. Okay. So what in the world is all of this? So this is the X. So this is my variable. This is my variable. This is the mean of the variable, and then this is the standard deviation. How can I make sense of this? So what I'm going to do, this is called tests of hypothesis or hypothesis testing, or test of significance. Let's call it that. Test of significance. So we are coming full circle. By next week, you'll see it all comes together because we're going to talk about significance, tests of significance, or hypothesis testing. I'll say the other word here is test of hypothesis testing. And I'm putting it in columns because I'm going to do it again and again and again. So what I'm going to do, because I don't know P, I'm going to guess what it is. I'm going to say, and I'm going to go step by step to show you this. I'm going to say, I don't know P, but I hypothesize that it is some value P0. And I'm going to explain that in a second. And as a result of I don't know it, but I'm going to assume it's P0. So suddenly I can do what I did over here, where I got P hat out of a sample, and then I started using it as though it was P. Well, I'm going to do the same thing here. I'm going to treat it like it's P. And I'm going to compare it to what? Well, I'm going to make a guess that I think it's P0. And then I'm going to test it like I promised you. I'm going to try and find evidence against it. The evidence is going to come from a sample. So from a sample, I'm going to calculate the sample statistic P hat. And I'm going to see how many standard deviations are they apart from each other. So I'm going to standardize P hat. So I'm going to minus off this value and divide by the standard deviation and see if it's an outlier. That's what I'm going to do. Okay, so I'm going to guess. Okay, so I'm going to go through the steps. And if you have to go, you guys can get going, but I'll do the one example and then I'll go for today. So you'll have the complete example to work and review, to work with and review. Okay, so I'm going to do one exercise like this, and then you'll have many to repeat. So I'm going to use the example that I have in the notes. About vitamins. Okay, like I said, if you have to go, you can just go, but I'll finish this and you can look back at it. And it's also in the other videos. This is my classic example. So what I'm going to do are 5 steps to solving this, and it might not make you happy, but once you get the conclusion, you're going to be happy. I know it's kind of corny, but anyway, I need 5 steps to do this. And this is a long way. There's going to be shorter ways to do this in certain conditions or circumstances, but I'm going to go the long way. And I begin with H. H is the hypotheses, because there's 2. First is known as the null hypothesis. This is a statement of the status quo. So this is what we believe. We might or might not have strong evidence from the past about something, but it's what people believe, okay, goes into the null hypothesis. And so that's going to be our assumption. And then we're going to look for evidence in a sample against this assumption. So in our case, the statement of the status quo is going to be that, this is a colon. Is that P, the true proportion is what? So we have to read this problem. A random sample of 900 individuals, so what's 900 going to represent, has been selected from a large population. It's found that 180 are regular users of vitamins. Test a suspicion that less than 25% of people use vitamins. So what I put here is what I'm going to assume the status quo, well, I'm going to assume the status quo belief is, and then what I'm going to put here, this is called the alternative hypothesis. And I'm going to teach you how not to mess this up. In general, this is what I do. I have to read this problem and figure out what number goes here. Whatever number goes here also goes here. What is the alternative? The alternative hypothesis is what I believe to be true if there's evidence to reject the null hypothesis. And I have to put a sign in here. Either I put the opposite, not equals, I make it greater, or I make it less. Those are 3 options that go in there. So the proportion, I have to pick one number that goes here, and this is going to be what I believe to be true if I find evidence against the null. So what number should it be?
More than 25%?
No, just the number, not the sign yet, just the number. What number?
25?
Yes, 25%. So this is going to be 0.25, and the number I put here, I'm also going to put here. And then now you tell me what I put there is the alternative. So notice I can only put an equal, the way I'm teaching you, you can only put an equal sign in the null, an exact assumption, because otherwise I can't use the theory. It has to be equals. So what I put here is my suspicion that less than 25% of people use. So that is going to be this. That's my selection. I'm going to select less than. Okay. I don't want to confuse you, but okay, that has to be less. All right. So that's the rule. So the rule is it's always going to look like this. And whatever number I put here, and this must be an equal sign in the null. Because that's really important, because the next step needs it.
Sorry, but wasn't the suspicion the belief? So the belief was less than 25?
Less than 25%.
So the alternative would be more than 25, right?
No, the suspicion is being tested. So we're going to assume this is true, and then we're going to look for evidence against it. And then if there is, we're going to find that less than 25%. We're going to say we have evidence that less than 25% use vitamins. So the second step is oh geez, I always mess up here. So that, no, I gotta make this bigger. A for assume. Assume what? We can't do anything unless we assume we know P. Assume H naught is true. In other words, P is equal to what we're going to call, this is P0, the hypothesized, the null hypothesis of 25%. So we are going to assume it's 25%. And then what can we expect? We expect that a sample result will be approximately normal with a mean of P, in our case, equals to 25%, and a standard deviation of P, 1 minus P over N square root, which is 0.25 times 0.75 divided by N. What is N?
100? The sample?
Yeah, well, what is it?
Sample 900, right?
900. So when you compute, what is the standard deviation of P hat? To 4 decimal places, it's 0.144. No, I did it wrong. 0.0144. Right, Marla. Okay, so I have the mean. I have the standard deviation. And it's all possible. I don't have to call it a standard error because I have assumed this to be true. So it's called a standard deviation of P hat. And now what do I do? Well, now I look at my evidence. The next step is called the A step. This is making me crazy. These relative measures of the width. Okay, so now I want to do the second A. I want to assess the the evidence. What is the evidence? It's what's from the sample, right? We took a sample. And what did we get? N was 900. X was what?
180.
Right. So then what is P hat? You have to keep it in your head, separating the sample result and the population result. Always, always separate those in your mind. Okay, so we got 20%. We got 20%. So the question becomes, is this evidence against 25%? How will we figure that out? Well, P hat has a distribution. And the distribution has a mean of 25, but it has some variation. Right? It's not always going to be 25 in different samples, but on average, it's going to be 25 over all the samples with this kind of variation. So there's going to be a difference. Now, what we have to figure out is if 20% is outside normal, we have to see if 20% is an outlier. That's what we have to do. So we're going to assess the evidence by calculating the Z. Z is equal to, X minus mean divided by standard deviation. In our case, we're going to standardize P hat minus its mean divided by its standard deviation. So P hat is 0.2. Its mean was above 0.25. And its standard deviation is this. So we already have everything that we need. 0.25 divided by 0.0144. So how many standard deviations are they apart? Aha. What do you think about that, Patricia? Is that too far? Is that too different? Well, it's an outlier, right? It's an outlier. So from what we've known so far, I'm going to teach you a little bit more about how to be precise in your reporting, but this is evidence against the assumption. This is evidence that we found something bizarre, right, in our sample. It's not that there's something wrong with the sample, it's something is wrong with the assumption. So we're going to end up throwing out the assumption. We're going to reject the assumption, and we're going to make a statement that we have evidence that the alternative may be true. We have evidence, at least on the sample, that it's less than 25%. It's actually 20% for this sample. But because there's variation from sample to sample to sample, we can't say it is 20%. We're going to say there's evidence that it's less than 25. So I'm going crazy with my font size. But anyway, this will be, you can see that, right? So we move to P, the P step. We're going to convert this into a probability. Any questions so far? So everyone's made all the calculation, you wrote this down, or you're just watching me. Are there any questions so far? So we assessed the evidence, we just did the math. And now what we're gonna do is calculate the probability of seeing this. The p-value means the probability of seeing a test statistic, that's what that's called. I have to tell you that. Z is a statistic, right? We're going to call it the test statistic. It's a statistic because I'm calculating it from the results of a sample. The probability of seeing a test statistic as extreme or more extreme given H naught is true. So given the assumption and being able to standardize, we found out something's wrong. It's very strange what we got. So how strange? I'm at negative 3.47. And what's the chance of being as extreme or more extreme? To understand what I'm talking about, you have to go back to the alternative. I haven't used this at all yet. I'm going to use it now. Okay, so this alternative hypothesis gets used, the symbol gets used over here in P. I'm going to go left. And I want to find out what's the probability of being here. I'll use a different color so I don't confuse you. So what's the probability of being here? This is my p-value.
Very close to 0.
Right. It's close to 0, right? If we use our table, what do we get? Go to the table. So we're converting number of standard deviations from the mean to a percentile. So we want the percentile. We want the tail value, the tail probability. That's another way to speak of it. You go to the table. And you're going to negative 3.47 and you get this. 0.0003, very small number, very close to 0. I could also do it in Excel if I wanted. So the p-value is actually equal to the value .0003. So the chance of seeing a test statistic, given the assumption of 25% proportion using vitamins, is very small. It's 0.03% or 0.0003. So I'm just repeating that I know that it's an outlier, but I have more specific, I have to be more specific because we have a standard for comparing. This is the concluding step. In general, the conclusion looks like this. P-value less than or equal to alpha means reject. H0. What is alpha? This is called the level of significance. Who's going to establish how bizarre a number is? Is 0.03% small and unusual? Like who establishes that? What is the standard for rare or unusual?
Usually 95% confidence, it would be 0.05.
So we have a standard that we usually use, and usually we put point, if it's not told to you, if you're not given a level of significance, okay, you use a 5%. Okay, so you put the p-value in here, 0.0003, and you assess it. Since 0.0003 is less than or equal to 0.05, you reject the null, and you say you found something new. You found something interesting, because the status quo belief, the belief was that it should be 25%, but we were suspicious and we found evidence to refute the 25%. So we have something to report. We have an article that we can write and we can publish. We can put it in El Nuevo Dia. We can put it in a medical journal if we think it has a quality of research that meets the standard. But this is called a significant result. Okay, so we say test is significant. So by falsifying and rejecting the assumption, you find something groundbreaking. Now, you can also report when you don't have a significant test, if that's interest to people, but usually you want to find something new. You want to report something new, right? You don't necessarily want to just say, oh, I got the same as everybody else. But anyway, depends. There's a tendency to want to report something new in science. So we say in words, so I'm going to ask you to write your answers in words. There is sufficient evidence to suggest that less than 25%. Now, I don't talk about the 20%. I use it for my calculations, but I know it's just one sample and I could have had another one. But I go back to my statement of all the alternative and I say there is sufficient evidence to suggest that less than 25% of people use vitamins. So you can say test is significant. You can write this. You can do this in numerical, a numerical way. But in general, this is how you test. Oh, wait. This is how you conclude, in other words. And I have to tell you a couple of other things. First, what if you don't get to reject? If you don't get to reject, what you write is, if the p-value is not less than the alpha, then you say you failed to reject. You didn't find evidence against. And I need to white this out. Need to figure out how to get rid of that shadow. So that's one thing I have to tell you. So in this case, you cannot, if that happens, that you don't have a p-value that shows or demonstrates what you got is rare, then you would fail to reject. You haven't found any significant evidence and test is not significant. Oh my goodness. And you can practice that. And the other thing to tell you is, well, you have to practice. What if we have a different alternative, not just the left side? What if we go on the right side? If we go on the right side, we get the p-value in the upper tail. What if we don't go on the right or the left, we go on both? We have to check in both tails. So I have examples on the other situations for you, but it's essentially always going to be this conclusion that you use, you test against. If this is not true, then this is the case, fail to reject. All right, so that's my first example, and you're going to see many more. I'm glad we were able to do this so early, and you guys can get going. So you need to go back and make sure you review sampling distribution of a statistic, that you practice the inference on a proportion. And next class, I'm going to answer your questions, and also we will look at 5 and 6, which will be very easy. I'll talk about the t-table some more as well. Any questions for me? So this is going to get very repetitive with a little twist here and there. I'm going to just do these 3 sorts of problems again and again. Okay. And I will put a connect assignment, Patricia. Yeah, I'm going to put it up. Yes, the test will be on July 8th. Yeah, I didn't change that. I can't change that. I think I set that date. I have to do it on that date. Yeah, did I say, do I have enough time? Because I have to see, because I think that has to be the due date, right? Because I have to hand in grades. Let me double check that point that you just made. I think I looked at it, but let's be sure. Because I think 8th might have to be the due date. Thanks for checking me. Oh, yeah. Hold on, Marcos. Tercer trimestre. Okay, the grades must be in. Oh yeah, I have time. I can post it on the 8th. And you can have 72 hours, yeah. Okay.
Be enough time to review after the 72 hours? Or do you have to?
Me? Because the deadline is the 15th, so I have time.
Yeah, but also with us as a team, like we did last time.
Oh. Well, classes are over, but I mean, we can set up a meeting, I guess, yeah. If you really want to look at it together. Okay, and the next Connect assignment should be on so looking at the schedule, chapters some things in 6 and 8, 20, 9 and 10. Anyway, it's all those ones listed there on in the module 8 and 9. Okay. Go use that table that I made to help you. I think Friday I'll make it due. Yeah. So for module 8s and 9s chapters. Oh, and I'm going to open up some assignments for module 7 too. Some practice assignments. I saw that I didn't have enough. I have some more to put up. Okay, so let me go and I'm going to post this video and you guys continue studying, okay? We'll talk soon. Have a good afternoon. Thank you.
Thank you. Good afternoon.